Continuing with our discussion of background, we're going to be talking about relations, functions, and operations. Well, what are relations? Okay, again, this is supposed to be review. You don't have to immediately be 100% familiar, but hopefully the terms are at least things you've heard before. If not, go back and look at the Discrete Mathematics Uncovered series. It covers all of these topics in much more detail. Well, if you have two sets A and B, and R is a subset of the product set, that's called a relation. Specifically, okay, we have a subset of A times B, so we have certain ordered pairs. Whatever ordered pair belongs to the relation R, we say that the first element is related to the second by the relation, and that's typically how we talk about relations. It's uncommon to talk about relations as ordered pairs. That's their formal definition, but we typically say there's some sort of, well, relationship between the two objects. Okay, you can also write A is related to B as just ARB. Now, on a formal level, any subset of the product set is a relation. But in practice, we're going to use some sort of special property to define it. For example, if A is all the words in the English language and B is the set of letters, we could define a relation by saying a word is related to a letter when the letter is in the word. So balloon is related to B, A, L, O, and N, but not to X, because the letters B, A, L, O, and N are in that word, and X is not. Okay, we can talk about equivalence relations. When R is a relation from a set to itself, so we're now talking about things in a set being related to things in that same set, each of the following can be defined. We can say the relation is reflexive if everything is related to itself, and it'll depend on the relation. This might be true and it might not. Okay, a relation is called symmetric if whenever A is related to B, then B must be related to A. So if the relationship points in one direction, it must point in the other. There's no distinguishing left versus right when we write that relation. And again, not every relation is going to have this property, but some might. And a relation can be called transitive if whenever A is related to B and B is related to C, then you can conclude that A must be related to C. So if you have a sort of chain of relations, A goes to B and B goes to C, then you can cut out that middleman of B and just say A goes directly to C. And again, not every relation has this property, but some might. If, however, you have a relation that has all of these, it's called an equivalence relation. It is reflexive, symmetric, and transitive. It's reflexive, everything's related to itself. It's symmetric. If one thing is related to a second, then the second is related to the first. It's transitive. If one is related to a second and that second is related to a third, then the first is related to the third. If you have all three of these properties, you're called an equivalence relation. So it's got to have all of those properties. And symmetry and transitivity are conditional statements. Reflexivity is not. Okay, here we have a conditional statement. If A is related to B, then B is related to A. Here we have a conditional statement. If both of these things are true, then this one is as well. Reflexivity is not a conditional statement, which means it's generally proved in a different way. What are equivalence classes? Suppose you have an equivalence relation. So it is reflexive for every A is related to itself. It is symmetric for every A and B. If A is related to B, then B is related to A. And it is transitive for any A, B, and C. If A is related to B and B is related to C, then A is related to C. So we've got an equivalence relation. Then for any element of the set, we can talk about the equivalence class, and we use these square brackets. The equivalence class of A is the set of things related to A. So it's the set of everything related to A. That's the equivalence class of A, and it only makes sense to discuss this when you have an equivalence relation. Well, one thing that one can show is that two equivalence classes, if their intersection isn't empty, then they are exactly the same set. So this is the set of everything related to A. This is the set of everything related to B. If I assume their intersection isn't empty, there is something in both sets. There is something that's related to A and is also related to B. What you can prove is that these are the same set. Okay? Anything related to A is also related to B and vice versa. Okay. What this tells us is that equivalence classes partition A into a collection of sets, the equivalence classes. And vice versa. Any partition of A can be used to define an equivalence relation. If you split the set A into a bunch of pieces, you simply define a relation by saying the two things are related when they're in the same piece. So equivalence relations can be viewed as partitions, okay, collections into equivalence classes. And again, this was all covered in the discrete math series. Hopefully it's vaguely familiar to you. One example is that integers can be partitioned into evens versus odds, forming two equivalence classes. One equivalence class is all of the even numbers, and one equivalence class is all of the odd numbers. This is a pretty obvious way to partition the integers into two sets, and we can use that to define a relation. Well, what's a function? If A and B are sets and I have a relation from A to B with two distinct properties, for any element of A there is exactly one thing that it is related to, then we say that it is a function from A to B. Typically we're going to use lowercase letters for functions, f, g, and so forth, like we're used to using. And if f relates A to B, what we write is f of A equals B. This is our traditional function notation. Now what's important is that for everything in the set on the left, there is one thing that it's related to. That is what justifies using this equal sign here. F of A is only related to one thing, B. So I'm going to say those two things are equal. If A was related to more than one thing, I would have a problem if I tried to use equal signs here. The set A is called the domain, and the set B is called the codomain, and we can write f A arrow to B. Notice this arrow has a little foot on the left side to distinguish it from a logical implication arrow. Most people, when handwriting, may just use a straight arrow here. Technically, it's a slightly different symbol. Okay, we also could say this out loud as f maps A to B. So notice that since every A is related to exactly one element of B, if f of A equals B and f of A equals C, A is related to B, A is related to C, but A was only related to one thing, so B and C must be equal. Okay? That's really what justifies using the equal sign here. The range of the function, notice up here, I didn't say B is called the range, I said it's the codomain, because it's not quite the same thing. The range is a subset of the codomain, given by elements of the codomain so that there exists something in the domain mapped to that B. So the range is stuff in the codomain that is actually f of something. The range is the elements that are actually related to something by f. The codomain B might have more stuff, more elements that are kind of irrelevant as far as the function is concerned because it's never actually achieved as a value of the function. But every element of the domain must be related to something. That is part of the definition of being a function. So not every element of the codomain must be related to something back in the domain, but everything in the domain must be related to exactly one thing in the codomain. As I mentioned before, the word map is often used instead of relate. So instead of saying f of A equals B, instead of saying A is related to B, we might say A is mapped to B by the function f. And we can say that out loud as f maps the set A to the set B. Well, now that we've talked about what functions are, we can talk about special types of functions, specifically injective and surjective functions. Suppose I have f, which maps the set A to B, a function. So f is a function, its domain is A, its codomain is B, and the range is therefore a subset of B. A function is called injective if, for any two elements of the domain, if I assume that their values in the range are equal, then I must have started with the same thing in the domain. If f of two things are equal, then they started out as equal. That's called an injective function. Notice, if the output of the function is the same, then the input must have been the same. The contrapositive of this statement, if the inputs were different, then the outputs are different. Injective functions are also called into, and you can say, for example, f maps A into B, and you would say that's an injective function. If f is injective, we can talk about an inverse. Okay? Since there was only one thing that got mapped to a specific element, we can talk about the inverse image of that element. So if f of A equals B, and we have an injective function, I can say f inverse of B equals A. This is a function that goes from B back to A. Conversely, a function is called surjective if for any element of the codomain there does exist something that gets mapped there. In other words, for every element of the codomain, it's actually in the range. Surjective functions are also called onto, as in f maps A onto B. That would be a way of describing a surjective function. And when a function is both injective and surjective, it's either called bijective or one-to-one. A bijective function takes a single element of the domain A and assigns to it a unique element of the codomain B, and vice versa. Every element of the codomain B is actually in the range, meaning it is achieved as some value of the function. There's an injective map from A into B if and only if the cardinality of A is not larger than the cardinality of B. There's a surjective map if and only if the cardinality of A is not smaller than the cardinality of B, and there's a bijection when they have the same cardinality. Cardinality is a set theory term describing how big sets are, and the definition is really in terms of injective and bijective functions. Well, what are operations? Suppose I have a function that takes ordered pairs of the same set and outputs a single element of the same set. That's called an operation. Now that sounds very strange, but believe me, you've done it many times. For example, summation and products of integers are operations. Now when I have a common operation like summing or multiplication, we tend not to use function notation. Why is summation an operation? Down here, I would say, take the ordered pair 3, 2, and apply the summation function. What is the sum of 3 and 2? It is 5. I plugged in an ordered pair, and I got out a single number. That's an operation. But we would usually just write it like this, 3 plus 2 equals 5. But this really does refer to, here is the summation operator, act on these two numbers to produce this single number. So it acts on two numbers and outputs a single one. That does make it an operation on integers. Now operations like summing or taking products or others might have the following properties, but also might not. Could be associative. In function notation, it's written like this, and this looks very strange, but here's what it says. Act, if I have 3 elements, act on the first 2. Now this is a single number. Then act on that third one. That will be the same thing as if I had first acted on the second pair of numbers, producing a different thing, and then act on A with it. In summation, for example, first add A and B and then add the third one, or first add B and C and then add the first one. If that result is always the same, it's called associative, and for sums, the associative property is true. The commutative property would say the ordered pair you plug in, you can plug in either order. If you act on the ordered pair AB, you get out the same thing as if you'd acted on the ordered pair BA. And for products, for example, this is true. A times B is the same as B times A. It's also true for sums, but it might not be true for others. Okay, so some operations, for example, are not commutative. You may be familiar with matrix multiplication, in which case A times B is not the same as B times A. But exponentiation is also an operation on natural numbers excluding 0. And A to the B is different from B to the A. So it kind of matters which of these two numbers is the base and which is the exponent. So exponentiation is not commutative like this. It also, by the way, is not associative. A to the B to the C is different from A to the B to the C. Okay, some operations might not be associative. Exponentiation, I mentioned, is not. Okay, if you have A to the B to the C, that's not in general going to be the same thing as A to the B to the C. So exponentiation is also not associative, but it's a little unusual to talk about it in those terms, especially at this point in your math careers. Typically, we don't talk about non-associative operations, and when we have non-associative things, we tend to just not call them operations to not muddy the water. But there we have it. Well, what are identity elements? Suppose I have an operation. If there is something that has the property that when I act on A with this special thing E, I always get back out A, that's called a right identity element. A acting on E always produces A. If I have E acting on A always produces A, E is called a left identity element. If it's both a left and right identity element, we call it an identity element. If you act on something with this special thing E, either from the left or the right, you don't actually change the value. Acting on it on the right doesn't change the value. Acting on it on the left doesn't change the value. That's called an identity element. Properties of what identity elements are and aren't and what other things they might do isn't really our concern. This would be something you would take up in abstract algebra, a topic called group theory. But one important fact is that if F has an identity element, it only has one. And you've encountered identity elements before. For addition, 0. If you add 0 on the right or you add 0 on the left, it doesn't matter. You don't change the value of what we started with. And for multiplication, 1. If you multiply by 1 on the right or you multiply by 1 on the left, you don't change the value. So 0 is the additive identity, the identity element for addition, and 1 is the multiplicative identity, the identity element for multiplication. For exponentiation, however, 1 is a right identity element. A to the first is going to equal A, but it's not a left identity. 1 to the A is not equal to A, it's equal to 1. So 1 is a right identity, but not a left identity. There is no left identity for exponentiation, and this is because, or related to the fact, that exponentiation is not commutative. So putting the A to the first is just a different thing than 1 to the A. Since exponentiation is not commutative, just because acting on the right is identity does not necessarily mean that acting on the left is. And as I mentioned, there is no left identity for exponentiation. For matrix multiplication, the identity matrix is the identity for both left and right multiplication. Well, we talked briefly about inverse functions. So what about inverse operations? Suppose f and g are operations. With this way of writing in terms of functional notation, if a and b are acted on by the operation g, then f takes that output and acts on it with b, you get back this element a. You would say that f is the left inverse of g, or g is a right inverse of f. Okay. What this really says is g acts on something with b. F acts on that with B, and it cancels out, and you get back to the identity, to the element, A, that you started with. So for example, for summation, the inverse operation is subtraction. Okay. F of A plus B is going to be the sum, F of AB is the sum, A plus B. G of AB is going to be the difference, A minus B. Observe, by the way, that subtraction is not commutative. A minus B is very different from B minus A. But in any case, if I do this huge, ugly function composition, g of AB plus B, that would be the sum f, but g of AB is A minus B, and using properties of addition and subtraction, A minus B plus B would just be A. And if I tried acting in the other order, g of two things is to take the difference, but f of two things is to take the sum, and again, the b's are going to cancel out and I get out A. Summation and subtraction are inverse operations of one another, no big surprise. Okay. We're really only going to be concerned with inverse operations a couple of times in the course. This is a very, very isolated event. So if this is something you haven't looked at before, I wouldn't be too concerned. Okay. We are going to bring it up. It's not totally unconnected to the rest of math. You can discuss these things in abstract terms like we've done here, but we're only going to do it once, maybe twice, other than the ones that you already know, like subtraction cancels addition. Hopefully that's not a big surprise. So if this was totally new and scary sounding, don't be too concerned, okay? Just remember this is kind of an idea that we might want to revisit. An operation is a thing we might be interested in undoing. That's all we're really getting at here.